Okay, but there are certain things, there's certain reactions that are symmetry breaking, and I'm not exactly sure which they are. This is a symmetrical reaction. Obviously, there are some reactions that created matter but didn't create antimatter. They violated these conservation laws under certain conditions. These are called symmetry breaking reactions, and people get PhDs for figuring out what these things are, but there are some. Okay, otherwise there'd be nothing, right? Yes?
So wait, couldn't it just be the thing that, like, all the hadrons are on this side of the universe and all the antihadrons are over there?
But it's not, because we can look over there and it's all hadrons over there too. So.
But how do you know, though?
Right. Yeah. I mean, maybe. I mean, this is generally people don't believe that, and maybe I don't know how to answer why. Right. Because if we're seeing a proton's worth of an Earth-sized universe, certainly there's parts we'll never know. So maybe it's over there, but they don't think so. I think it's because it's pretty well mixed. The universe was pretty small when this happened, right? So it was all pretty well mixed, right? So I think that's probably the answer, but I'm not sure. Okay.
I was told at one time, like, one of the reasons we have so much problems discovering dark matter is because, you know, we're made of matter. And how do you look at something with matter when it's made of dark matter? You know, it's like,
well, the dark matter is non-baryonic stuff. It's not made of baryons. It's not hadrons. It's not normal stuff. It's some exotic thing that we are working on, right?
Yeah, but isn't antimatter just like the exact opposite of matter? Would we have trouble looking at it as well?
No, not really. I mean, yeah. Basically, antimatter is really easy to figure out because when it hits matter, it annihilates and creates these signature photons that you can isolate. You go, oh yeah, that was a positron annihilation, right? So we don't really have a problem detecting antimatter. We just do it indirectly, right?
I'm just wondering that maybe there's like an antimatter galaxy over there that we just can't.
Right. Certainly not in the visible universe. In the visible universe, we could see an antimatter galaxy, and we could determine that it is an antimatter galaxy, and we haven't seen that, right? It might be that it's beyond our proton's worth that we can see of the Earth-sized universe, right? But I don't think so. I don't think anybody believes that, but I'm not sure why not, right? Okay, so, well, I don't think it's that they don't know. I think it's that, I mean, I've never heard that, so. Okay, so let's do some calculations here. Here's the notion then, right, is that we start out with a ton of energy per photon. We can create any particle we want to. We can create Higgs bosons. We can create anything, right? Okay, and then as the universe cools down, the photons lose energy. They're able to create less and less massive objects. When it suddenly drops below the lightest of a particular type of particle, right, then you can no longer create those particles. So here is things like protons, right? Here is things like electrons. Electrons require much less energy to create. And then ultimately, you actually condense, you go from plasma to matter. So these are all important temperatures. Let's calculate those temperatures. And that's what's in your little note guide on the other side. Here. Okay, so there's this. You've labeled this thing. Right here, proton creation energy of about 2 giga electron volts, right? And protons are the lightest of the, I should get this right. I think they're baryons, are they? Okay, let's go. I've got a little chart here. There we go. Yeah, baryons. Protons are the lightest of the baryons. Okay. Okay, so let's calculate these things. The first one is 2 giga electron volts. If you drop below 2 giga electron volts, you no longer have the ability to make a proton. Okay, so let's calculate that energy. Okay, so the first thing I'm going to do is I'm going to go 2 times 10 to the 9th, and this is electron volts, right? And I'm going to go that times 1.602 times 10 to the minus 19th, and that's going to give me joules, right? So let's do that. Take your calculator out and touch your calculator. It'll help you wake up. Wake up! Wake up! Nick! Well, get your calculator out. It calculates something. 2E9 times 1.602. .204 times 10 to the minus 4th or minus 10th joules, yes? So the next thing to do is to figure out the wavelength of that. Yeah? We're going to figure out the temperature that corresponds to average photons that have an ability to create protons willy-nilly. Yeah? So it's got to have 2 giga electron volts, and that's because a proton has a rest mass of 938 million electron volts. which is roughly a 1 giga electron volt, yeah? Yes? Yes? So we basically need an energy of 2 giga electron volts to create a pair of them, don't we? Unit of energy, yes.
Oh, okay.
That's right. There are no stupid questions. All right. So basically, this energy, if you've got this energy, you've got enough energy to create a proton and an antiproton, right? And that's what we're talking about, this pair production, right? So there's our energy in joules. Now let's figure out the wavelength. If energy is hc over lambda, then lambda is hc over energy, right? So I'm going to plug this number in for our energy. Okay, so 6.626 times 10 to the minus 34th, right? Times the speed of light, 3e8, right? Divided by 3.204 times 10 to the minus 10th. Let's figure out the wavelength now. It's very, very complicated. Right? Times 3e8 divided by the answer I just got. And I'm getting that the wavelength is sweet mother of the Savior. There's our wavelength. Now, what temperature does that correspond to? This is a black body curve. This is, let's just say that's the peak. Let's plug it into this thing. What temperature is it, right? So I'm going to go, the temperature is this divided by this, right? So it's 2.9 times 10 to the minus third meters Kelvin divided by 6.204 e to the minus 16th meters. Yeah? So 2.9 e minus 3 divided by the answer I just got. And I'm getting that it's about 5 times 10 to the 12th. 5 times 10 to the 12th kelvins. That's pretty hot, isn't it? Do you suppose that's this temperature right there? Yeah, label that. 5 times 10 to the 12th kelvins is right there. Yeah? At below that temperature, the average photon energy, you can no longer create hadrons. Okay? You can no longer create protons, and so therefore all the protons that ever were created by the Big Bang were created before that. Okay? After that, no more creation of them, right? Yeah, because it's too cool. Yeah?
So, in the original, it says 2 times 938 million electron volts.
Uh-huh.
And you just did
2 giga electron volts. That's close enough, isn't it? 938 million electron volts is roughly a giga.
Yeah, I know. But if you did the 938, would you get a different answer?
Yeah, slightly different answer. It's very close, though, right? We're getting ballpark, right? Are we good? So there's that calculation. Let's do our next one. Our next calculation is the energy to create an electron and a positron. These are the lightest leptons that there are. There's heavier ones, but these ones are the lightest ones. So let's do the same exact calculation for that, right? And figure out the temperature, right? So the wavelength is going to be hc over E, isn't it? Right? So that's going to be hc over the energy in electron volts, right? Times the electron charge, right? Isn't that right? And then the wavelength, the temperature is going to be 2.90 divided by hc over the energy in electron volts times E. I'm just doing this because then we can just like type something in, right? Okay. So let's go 2.9 E minus 3 divided by, now we need a parenthesis, right? And I'm going to go 6.626 E minus 34 times 3E8. Okay. Divided by, now you need to put this guy in parentheses, this denominator, right? In parentheses. So divided by parentheses. And what's the energy? What's the energy to create a positron and an electron? What did I say on there? About 1 million electron volts, a little bit more, right? So if you want to be accurate, you could use the thing, right? I'm just going to put 1 million electron volts in. So I'm going to go 2.9 E minus 3 divided by 6.626 E minus 30.